Much of today's scientific knowledge was acquired by pure luck. Neutrinos are extremely elusive and complex particles that were discovered only with the assistance of such fortune. In a few seconds, the sun emits more neutrinos than all the grains of sand on all the beaches of the world. This means that 66 billion neutrinos pass through your eyeball every second, but they will rarely ever interact with any matter. To understand what these particles are, one must first understand what radiation is. Radioactive decay happens because all matter tends to convert itself into the lowest state of energy possible. Alpha decay occurs when an unstable isotope reduces its atomic number by releasing 2 protons and 2 neutrons from its nucleus. This helium positive 2 particle is known as an alpha particle. Being rather large, it easily interacts with other matter and gains 2 electrons to form a stable helium atom. Beta decay occurs when an unstable isotope converts a proton into a neutron by the release of a negative charge that manifests as an electron. Energy and matter can be converted into each other because of Einstein's energy-mass equivalence formula, E equals mc squared. In a sense, mass is just a highly dense bundle of energy. With careful calculating, scientists of the day noticed something. Not all of the energy lost during beta decay was accounted for by the formation of an electron. Even more surprising, this deficit seemed to vary from almost nothing at all to a great sum of that lost energy. Scientists began to question the most fundamental law of nature, the law of conservation of energy. Wolfgang Pauli refused to accept these implications and theorized another explanation of the deficit. He suggested that another particle was emitted alongside the electron, a new ghost particle with a neutral charge. After much criticism by the scientific community, Pauli later proved that a particle must exist. He recorded the energy of many emitted electrons and noted that their energy spectrum had a sharp end where it almost reached the expected value. This proved that energy was not being created and destroyed randomly and followed the law of conservation of energy. The remaining energy must be accounted for in some fashion. Pauli then began to refer to his ghost particle as a neutrino. Wolfgang Pauli knew how difficult it would be, if not impossible, to detect neutrinos directly, and so he wagered a case of champagne to whoever could prove its existence. This prize would remain unclaimed until a quarter of a century later. Bruno Pontecorvo was as much a ghost physicist as neutrinos are ghost particles. His story is a tragic one, for his brilliance remained generally unnoticed. His political views drove him behind the Iron Curtain into the Soviet Union. Pontecorvo theorized that the ideal element to detect neutrinos would be chlorine. When a neutrino produced by a nuclear reactor interacts with a nucleus, it picks up a negative electric charge and becomes an electron. This change would be counterbalanced with the conversion of a neutrino into a proton, creating an atom of argon. Since argon is a noble gas, it will not react with the rest of the chlorine and could be easily separated from the solution. Unfortunately, the resources he had prevented him from attempting to experiment himself. However, one man did notice Pontecorvo's ideas, Ray Davis. Davis, an avid chemist, tested his idea with 4,000 liters of chlorine at the Brookhaven reactor in Long Island, New York. Unfortunately and unexpectedly, nuclear reactors produce antineutrinos. Antineutrinos are identical to neutrinos except for their quantum spin. Spin in quantum mechanics refers to how the particles rotate with respect to their trajectory. In quantum theory, no two particles may possess the same quantum number, which accounts for its position and spin. The spins and positions can only have finite numbers and are therefore quantized. Regular neutrinos are now known to have a left-hand spin, while antineutrinos have a right-hand spin. Because of this property, the antiparticles were invisible to Davis's detector. Antimatter had not been discovered at the time, and so Davis's experiments were viewed as a failure. Davis will re-enter the story again when solar neutrinos come into question. The reward for detecting neutrinos would go to a different team, Fred Rines and Clyde Cohen. These two conducted an experiment to find the neutrinos that would be known as Project Poltergeist. Using his knowledge of nuclear interaction, Rines predicted that phenomenon known as inverse beta decay would occur when a high-energy neutrino interacted with a proton. When this occurs, the neutrino is converted into a positron, an electron's antiparticle, and the proton then converts into a neutron to preserve the charge balance. Positrons are like electrons, except that they have a positive charge and an opposite spin. The positron will quickly annihilate itself with a nearby electron, converting the entirety of their mass into energy, and release gamma rays. The proton will then be absorbed back into the nucleus of an atom and likewise release a gamma ray. Rines predicted the delay between these two bursts to be about 5 microseconds. Luckily, the mysterious antineutrinos that were produced in the reactor do act in this way. In the summer of 1956, a delay of 5.5 microseconds was recorded by Project Poltergeist, confirming the existence of neutrinos. They contacted Pauli and claimed his long-standing bet, the case of champagne. Until this point in history, only rough speculations could be made about the properties of our sun. The light we see was produced in the sun's inner core and required 100,000 years to reach the surface. Therefore, the light on Earth is really 100,000 years old. How then do we know that the sun is actually still burning? How old is the sun anyway? How hot is its core? All of these questions could be answered with a newly developed science, neutrino astronomy. Hans Bethe theorized a nuclear reaction chain that could be the source of the sun's energy by using hydrogen, the most abundant element in the universe, as fuel. He called it the proton-proton chain. The proton-proton chain begins with the fusion of 2 protons into a deuteron, a proton and a neutron, a positron, and a neutrino. The deuteron readily absorbs another loose proton from a helium-3 atom. 2 of these helium-3 atoms fuse to form a stable helium-4 atom and 2 separate protons. Such a reaction would produce temperatures nearly 14 billion degrees and provide enough energy for the sun to burn for billions of years. These theories would inspire Davis to have a second try by attempting to solve the new solar neutrino problem. Unfortunately, Davis's chlorine reactor requires neutrinos of energy around 14 megaelectronvolts, while the primary neutrinos produced in the proton chain only have energies of about 1 megaelectronvolt. However, Ray Davis realized that since the sun had already been burning for so long, a large quantity of helium-4 must be present in the nuclear furnace. Because of this, there's a chance that a helium-3 and a helium-4 atom will fuse to make a beryllium-7 atom and a gamma photon. Then there is an even smaller chance that this beryllium-7 atom will fuse with a proton to create an atom of boron-8. This atom is highly unstable and will decay into a beryllium-8 atom by releasing a positron and a neutrino. This neutrino would have enough energy to excite the chlorine nucleus and release detectable gamma radiation. At this time, a man named John Bacall was studying nuclear physics at Caltech when he decided to calculate the rate of inverse beta decay for electrons in free flow. What he found showed that Davis's formation of beryllium-7 in the sun was 1,000 times easier than it had been previously predicted. This led to his alliance with Davis in the search of solar neutrinos. Now a part of Davis's team, Bacall suggested that a 400,000-liter tank of chlorine should be placed 1,370 meters underground to detect solar neutrinos. The apparatus would need to be buried so deep to protect it from background noise in the form of cosmic rays. These rays are simply a blend of electromagnetic radiation and high-energy particles. With this system, a handful of neutrinos would be detected each day. After a lot of research, the team acquired a plot of space in the Homestake mine that fit the bill for the size and depth. Bacall continued to refine his calculations, and by 1966, the apparatus was built and they were ready to test. While the formation of beryllium-7 is fairly common, Bacall predicted that only 1 in every 10 billion neutrinos would make it to the final boron-8 stage. Despite their efforts, the team found only about a third of the number of neutrinos that were expected. Bacall's calculations involved lengthy algorithms and complex computer programs. Few could comprehend them, but many criticized them as being a source of error. Willie Fowler, a renowned astrophysicist, challenged Davis to inject 500 atoms of argon into his 400,000-liter detector and then remove them. Davis did and extracted every single atom. Little known to anyone, both Bacall's calculations and Davis's detectors were accurate. The neutrinos themselves were the ones at fault.